to wait a couple minutes for more folks to join. It's the last day of the conference, so this is actually the last slot of the sessions. I appreciate you all being here, especially after the celebration yesterday. It's a little wild. This talk is about Lambda architecture, how it can be applied with Cosmos DB, one of the solutions Cosmos DB uses for handling big data. And we'll talk about the theory of Lambda architectures and how it can be simplified using Cosmos DB, because some of the challenges that it provides are best addressed by a combination of cloud solutions. It's in its most pure instance, if you may, it's highly theoretical, so it can be applied to many different kinds of architectures. Historically, it has been mostly solved using on-premise technologies. So we'll talk about specifically how it can be simplified, not having as many systems or services to manage or maintain, mostly using Cosmos DB and Azure Databricks, managed services for both data processing and data storage. So Cosmos DB, as you probably know, is a cloud managed database, non-relational database resource, and it can be applied to many different solutions, as non-relational databases don't have the constraint of a schema or mostly schema, and they use horizontal partitioning. Cosmos DB can be applied to a large variety of problems. It can be the solution, data storage solution at scale for many different kind of problems. The question is, how can this be applied to big data? We've gotten different use cases, including there's IoT use cases, there's application services, but for big data, there's a few particular considerations that we have to keep in mind. So this is a traditional example of a big data architecture. It divides the different use cases for the data between data processing and data storage. It abstracts out the data sources as a layer that just basically deals with the source, with the initiation, with the origin of the data itself. And as you may see, the components can be fairly flexible. If you have a data storage component, it can be either a relational database, a non-relational database, a cache storage layer. Then we have a couple components that deal with processing. So this can be hosted in either an application that just reads data from the data storage layer. It can be a streaming layer that does calculations on the go, like an HDFS layer. Then we move on to analytics and reporting, and just basically the serving layer of any big data architecture. This can be hosted on an orchestration platform, either a cloud platform, a set of managed services, or it can be hosted on architecture deployment infrastructure that can vary in many ways. It can be containerized applications. It can be VMs using some sort of orchestration software. This architecture can have a few challenges in the way it can be implemented based on how many components, moving components, are available there for the data processing layers. So the question we have to answer is big data too big of a challenge? There's business questions that require different kinds of data, like you have real-time data, historical data, patch aggregated data. They all can have different kinds of periodical access, different kinds of aggregation types. This kind of challenge is usually solved with streaming layers, HDFS, or any sort of custom application implementations. There's a combination of technologies between streaming components, data stores, serving layers, and there's just so many answers you can implement in an architecture that is built for big data processing. So as a result, big data and the infrastructure to process this amount of data can be complex to set up and manage. So the question here is, how can the cloud address these challenges? Well, what we can do to modernize big data processing is we can provide minimal manageability, flexible scalability, and flexibility in terms of data design. And we also need a pattern that provides the guidelines for these kind of solutions to come together and create a full system that can address some of these challenges. So what we chose to use as our framework or guidelines for implementing big data infrastructures is known as the Lambda architecture. Fairly recent architecture that provides two kinds of paths. We'll go into it in a little bit, but it's basically an architecture that addresses both real-time and batch aggregation data needs. It's meant to be as simple to implement and adaptable to any sort of technology platform and any sort of technology that you can throw at it. Some of the requirements of the Lambda architecture itself are problems that can be simplified using some cloud solutions. For example, one of the main goals, according to some of the literature out there around Lambda architectures, are tolerance to human errors. Just automate as many processes as possible and have the system in its own describe clearly what data flows are happening inside of the architecture itself. Tolerance to hardware crashes and just hardware difficulties by the means of redundancy, by the means of retry logics, and scalability and quick response time whenever the data volumes that are ingested change. So this can be solved with the cloud with the means of automated data processes using solutions like Azure Data Factory, using solutions like Cosmos DB's change feed. You can actually automate the processes that involve moving data from one component to another. And there are many components in a typical big data architecture. Managed cloud systems actually minimize the risk of hardware failures, or through the use of the cloud and distributed replicated systems, you can actually you can have guarantees on the high availability of the solution itself. Scalability and quick response time is something that can be addressed with serverless architecture, serverless infrastructures. The serverless infrastructures are usually in the form of a pool of resources that you can obtain, and this process is abstracted out by the cloud platforms, but you can obtain, use, and only charge or pay for what you are using at the moment. So a combination of these advantages, managed systems that range from the platform as a service to the serverless architecture, can be applied to this theory of dealing with different paths of data and different kinds of data requirements that the Lambda architecture presents. So let's talk a little bit about the differences in the resources that you can find in the cloud and how these can address some of these challenges. I just want every one of us to be on the same page on when we talk about different cloud architecture deployments and solutions that range in this gradient of options. So as opposed to on-premise, in the on-premise world, you have hardware notions to manage. If you buy a server, you need to understand what kind of components it contains, all the way down to the hardware level. Then installing an operating system on it and all the manageability challenges that it can provide, including updates on the operating system software. This thing is blinking a lot. Is that normal? Is the guy over there? No? Okay. I'm just going to ignore it for now. But operating system level challenges that often also include some security challenges that you have to address yourself or have someone assigned with a role of managing the system in its own. Then the application runtime, which can provide, when you're running different pieces of software on it, you have to understand the versions of it. You have to understand the different libraries and compatibility that are implied within these choices of application runtime. And then on top of that, you can host your application logic, which depends and is heavily tied to all the components underneath. And of course, the application runtime can abstract a lot of these decisions. It is important that for the additional measures, like including security, including scalability, you are the main responsible agent to change and optimize that for your workload. In an infrastructure as a service kind of provisioning model, you have only the operating system to manage. A VM is fairly equivalent between many cloud platforms and cloud solutions, but you still have a notion of an operating system. You know if your operating system is sort of a Linux operating system, a Windows operating system, which version, and that has implications like which version is in long-term support, which version is release candidate, Things like that you have to keep in mind when you are hosting software on top of an infrastructure as a service. Application runtime is something you also have to manually install and maintain, and all the implications with it that are related to the application logic. You talk about platform as a service, the operating system is abstracted out. You only know of the application runtime, and this is usually exposed as a configurable setting. So for example, if you are using Azure App Services, it'll provide a drop-down menu that contains which runtime of .NET, of Java, of JavaScript, is executing in the background. And usually you have some sort of flexibility, but you lose a lot of that power, a lot of that control by choosing a managed service like a platform as a service. Then one of the main things you have to worry about is the application logic that is running on top of that, but it often restricts your options on how you want to develop your applications because a lot of these decisions were already made for you. And then in a serverless architecture, in a way, you lose all of the power of choosing what are the components underneath it that will enable your application to run. But that also allows you the flexibility of actually changing your business logic continuously because you don't have to make all these decisions of actually managing the software and the platform underneath. So the perfect solution is not one of the spots within this gradient of options. It's usually a combination of many of these. And in Azure, we make sure that the options that are available in the cloud, either ranging from infrastructure as a service to serverless options, are heavily integrated in an environment that includes solutions from development to management of the platform, intelligence in the applications, and so of the sort. So let's analyze the Lambda architecture, and then we can see some of the challenges with it and how these can be solved by using cloud components. So the Lambda architecture, as you will see, splits the data in two paths. It abstracts out the data sources and how the data is ingested in the system. And it addresses two main needs, which is I want to know real-time insights on my data, and I want to know aggregated views on my data. What aggregated views? We don't know. It can be anything. It can have different periodical aggregation timing, or it can be something that needs to be highly configurable. So the data is pushed onto both layers, one at the top and one at the bottom. We're not talking about any infrastructural detail here. This is an abstracted, high-level architectural view of the system. The batch layer will include something that's the master data set. The master data set is an append-only database or data storage, just to not make it as specific as a database will contain it. This can be applied to any sort of infrastructure. Then the requirement of having a pre-compute layer that will obtain the data and then run data processing on top of it just so that it can push it to views that can later be queried by the end user or the end client applications. This is usually tied to the same architecture just to minimize latency, to the same, in a close relationship to where the data is hosted. And then you push that to the serving layer. The serving layer will contain what is talking directly with the database. Now, why separate these two databases? The reason is because usually the infrastructures will have different scale capacity. The latency that you will need on your end application, on your client application that is consuming the data all the way to the right side of the diagram, may have a different read rates than the ingestion rates that the master data set has. So usually these are addressed with different database products or different data serving products. On the bottom, talking about the speed layer, you have a real-time need of data. So usually what the literature suggests is to push the data directly onto a streaming layer or a layer that can provide real-time data directly onto the query engine. So the query engine will actually read the data directly from the source hosted on the speed layer with streaming computation if it's necessary, or real-time aggregations with whatever solution is used to host it. So I know that was a mouthful, but that is a high-level view of the architecture, and many different implementation details can happen within this model. So what are the challenges of implementing a model like this? Well, there are too many moving parts, as you may have seen. The there are different choices that need to happen and different implications with the technologies that are chosen. So for example, choosing a database for aggregate storage, real-time data processing, or the serving layer can be a challenge of its own just because you have to know what the requirements are for the specific querying patterns. Choosing a streaming technology for the speed layer, and then again, this sounds a little bit prescriptive, but streaming solutions are usually used for the speed layer, just in the way they provide the data from the source, computed on the fly, and then provided for the end user without having to store it, just because it's usually a lot of data to store. And then storing, one of the main reasons, one of the points that I was missing is that there is a need to store the data in order for the batch aggregations to happen. So you can't have historical data without having a data storage layer behind it that is going to provide that aggregated view, that predicated, let's just say, chunks of the data that need to be processed at a time. The serving layer for the real-time data actually needs to provide aggregated data on the fly, and the trade-off of storing that versus aggregating it on the fly are what this architecture means to address. So this often ends up in too many technologies, too many application or components to maintain. So you have to host each one of the databases that is used for the serving layer or the master data set or the streaming technologies. Separately, you have to choose how to host it. Is it on a platform as a service? Is it on an infrastructure as a service? So there is usually not a one-stop shop that can enable this architecture. So what is our value proposition here then? Well, we aim to simplify the Lambda architecture using Cosmos DB for many reasons in particular. Now, you need in a Lambda architecture different components with different data processing requirements, right? So for example, the speed layer needs to have real-time reads and real-time writes. That's why you use either something with a minimal data storage size or a stream processing layer. The batch layer requires a different, less frequent kind of read frequency and write frequency. You have periodical writes depending on, and often something you can configure, and depending on what your needs are for your data aggregation layer. Write frequency can also be periodical. You can have a job that is scheduled that reads the data in chunks and then aggregates that and provides that to the serving layer. And the master data set is usually the most challenging part of this architecture because it's a database that needs to be adapted to both the real-time and the periodical data set if the choice of a stream is not an option when serving the database, when serving the data from the source directly to the speed layer. So our proposal here is Cosmos DB can address these scenarios by providing tunable data querying by the use of different collections. I'll provide a quick reminder of Cosmos DB's capabilities in a little bit, but what the main value proposition is following. So you have service guarantees in Cosmos DB that will address the possibility of any of the components in the Lambda architecture to be faulty or to have, to provide downtime that will affect the entire system. As you may see, the system is highly connected. There's minimal latency and comprehensive SLAs that this system, that Cosmos DB provides. It can adapt to all sizes of databases. Cosmos DB uses horizontal partitioning to deal with data scale, so that can provide different collections with different sizes that will be either suitable for the master data set or for the aggregated views. We'll see in a second. Provides automatic data maneuvering through the change feed. Change feed we'll introduce in a little bit, but it's basically a kind of like an agent that runs on a database that executes logic upon every write or read. It integrates natively with data processing engines. We've made some investments in the Apache Spark layer specifically to address the data processing needs that can't happen directly in the database. And it integrates natively with the serverless components in Azure that allow for abstracted, isolated pieces of logic to isolated and stateless pieces of logic that can be executed on the data itself. So how do we apply Cosmos DB to the Lambda architecture? Well, first, we can make it be the master data set of this architecture. Now, as there is one master data set that has change feed. Change feed, as a reminder, can act as a streaming layer just because upon every write of the data, it can execute a piece of action. It can send it directly to a data processing layer, which can be Apache Spark. We recommend it to be Apache Spark just because it is natively integrated with Cosmos DB. So then that eliminates the need for having another component sitting in the bottom and only one target of the data as it comes through into the system. Then the serving layer can be a collection of Cosmos DB that is adequate in terms of throughput to the querying needs at the end of the architecture, at the other side of the pipeline. So in order to provide computed views, you can either host them on the database, but we also recommend using Spark just to read the data as it comes through in batches, then provide that and store the aggregates into a computed batch view that can be hosted in Cosmos DB and adapted to the querying needs. Or the query needs can happen directly against the master data set. So think about it this way. If you want to obtain the detailed view of the rows that you're aggregating, you can either query the master database directly, and you want a database that can actually serve both needs. You can query the master database directly, or if you want the computed aggregates that are generated by Spark, you can query the other collection that contains those views. They will have a less frequent reading pattern, and that's what can be tuned in Cosmos DB. I keep clicking on the wrong surface. And then in the end, you can have Spark provide the computed real-time view directly to the query, or have another Cosmos DB collection that contains these real-time queries that can be accessed directly by the application side, by the client side. So to simplify this entire diagram, we provided this view, which is centered on Cosmos DB and uses the same architecture on Spark to provide all of the data processing. So new data, this is the simplified view, new data goes directly into Cosmos DB. There's a master dataset collection, usually tuned to handle the large dataset that the append-only requirement of the data is generating. Then change feed replaces the streaming patterns that are often served by the lower part of the Lambda architecture and sends the data directly to Spark, which then provides the data onto the computed real-time views for a streaming layer that can be hosted on Spark, or the batch data that is then processed in Spark can be sent to a computed batch collection in Cosmos DB. And all these collections will have a throughput that is adequate to the specific reading and querying needs that the application requires for every single one of the collections. So they all have different scenarios. One of them is going to be accessed more frequently than others. The real-time view is going to be accessed at a real-time pace. The aggregated views will be more periodical, especially in reporting scenarios. And then in the end, everything is going to be sent to the query client at the end of the diagram. So I know this is a lot of data to consume at the moment, but we'll talk about every specific component and how it can work together. So how does Cosmos DB work for the master dataset and serving layer? Well, how many people here are familiar with Cosmos DB? Just a quick raise of hands. We can skip this slide then. Basically, we make use of the elastic throughput in Cosmos DB to tune every single one of the collections for the specific needs of the client application. But these three scenarios benefit from how Cosmos DB can serve multiple requests at a time. So as a reminder, for Cosmos DB, every collection has a set request unit per second that it can serve. So this means that how many requests in a second is this database capable of serving? For every one of the partitions, it can serve 10,000 requests in a second, and it can host 10 gigabytes of data. It can host data of any size through the use of this partitioning system, because you can just add on partitions as your throughput or data size requirements grow. So it makes it perfect for a master data solution. And often we get the question of why Cosmos DB and not a cold storage layer or a storage layer that is, for example, something of the sorts of Azure Data Lake or blob storage. The answer to that Basically, you still need a database engine that provides an indexed view of the data that is stored. So if you have a master data set and you have to process it in memory on a Spark layer or any other data processing layer, you don't want to bring the entire data set to be filtered in memory or to be processed in memory. You still need a database engine in the backend that is going to provide a predicate that you can pass predicates to. It will filter the data to the minimal amount of data you want to process in memory, and use that for your data processing, and afterwards serve it to the serving layer. This data can be filtered, as an example, this data can be filtered as a date view, it can be filtered as a where clause, and things of the sort. So, and this addresses the need for having a large data processing infrastructure sitting in front of your data storage layer. A large processing infrastructure is something of the sorts of, as an example, if you have 1 terabyte of data, you don't want to bring it into 1 terabyte of RAM or 1 terabyte of memory. That would be fairly expensive, and it might not even be necessary for the data processing needs that you may have. So this, the main point here is that different collections can adapt to the different needs, and Cosmos DB is flexible in a sense that if your data streams increase in size, and your total data storage is also increasing in size, it can be addressed by the horizontal partitioning. Let's talk about change feed for a second. So change feed here, in this case, is replacing the streaming part, the streaming component in the data layer. And what it really is, it's just a log that is stored with every Cosmos DB collection. So every collection has a list of writes and updates that happen against that collection. This is already enabled on all Cosmos DB accounts, and it can be used and it can be consumed to execute real-time operations as the data is inserted. So some of the benefits is that, well, as I mentioned, it's automatically enabled on all Cosmos DB accounts. It doesn't need any additional configuration. It can be consumed it can be consumed in ways that can be configurable. So we provide 2 libraries, the Cosmos DB SDK and it's called change feed processor library, just for different requirements of processing these logs. It uses the existing allocated RU, so you don't pay extra for whatever is being read on the change feed. And it's executed on insert and update operations. Delete support can be implemented through soft deletes, but we are working on a delete support for change feed, and it's coming soon. And it can be used as a streaming layer without requiring any other component. It just sends data directly as it is inserted. So change feed is also enabled per partition. So every partition will have its own change log, and every partition can be consumed independently. So just as an FYI, you can have every single consumer of the change feed work on each partition separately, which greatly improves the experience of ingesting data directly to the change feed from the change feed to the consumers. So this is done, if you want to learn more about this, this is done through the change feed processor library. It's a .NET library that horizontally provides parallelism when ingesting the data from every single one of the partitions. But there are other ways of implementing change feed. Change feed can work through Azure functions. There's a native integration that can trigger an Azure function, can be used as an input whenever an Azure function is executed, or it can be used as an output binding in an Azure function. And these are all completely managed options on the Azure functions interface. SQL API SDK will provide more control over how change feed is consumed. And just one of the examples of how this can be used is change feed, since it includes the entire history of all the data that is inserted in a database. And by reading the entire history, you can get to the latest state of the database. It can be consumed to migrate databases. So you can write an application that reads the change feed from the beginning of the time of the database, consume the entire database, and you will have a replica of that database as it is processed by change feed. And the change feed processor library achieves the same thing, but in a parallel distributed way. So you can have many threads processing the data and then handling the conflicts on their own as they process the data. So this component in the Lambda architecture is used as a scalable way to deal with the needs that the data processing requires. Let's talk about the data processing layer. So Cosmos DB and Apache Spark through Azure Databricks. How many people here are familiar with Spark? Just a quick raise of hands. Perfect. And what about Azure Databricks? Okay. So I don't need to explain this a lot then. Apache Spark is an open source cluster computing framework. It can be parallelized, so it provides scalable data processing through implicit parallelism. Simple programmability, it is hosted on two main environments, Scala and Python, and you can just import custom libraries. It's made so that it's extensible in a way that you can import custom libraries from the open source to use within your runtime environments that are running in parallel. It provides scale-out horizontal partitioning of nodes, which is perfect to be paired with a Cosmos DB solution, which is horizontal scale-out data storage. So you have both your data storage and your data processing to be scale-out components. So the main thing is that it provides a standard platform so you can process jobs in parallel and flexibly as clusters are provisioned with nodes that can provide that processing power, and it can be scaled up and down. Azure Databricks is a managed cloud solution for this particular library. So Azure Databricks is created their own runtime of Apache Spark. So it's an enhanced version of Apache Spark running on the Azure cloud. Now, what's the benefit of it running on the Azure cloud? A lot of the resources can be provisioned as they go through the main interface of Azure Databricks. So in the interface, you don't have to deal with VMs, application instances. You don't have to deal with any of the implementation details that the infrastructure requires as it is processing data. It's an easy-to-use interface, very similar to Jupyter Notebooks if you have played with Jupyter Notebooks before. Provides Python, SQL, and Scala environments, and it's highly configurable for library and runtime environment versions, which means that it is connected to the Maven Central and the PyPI repository, so you can download packages directly onto the infrastructure. It's made for collaborative work through the use of notebooks in Azure Databricks. In Cosmos DB, we have invested in a driver that is natively integrated with Spark for the specific scenario of scale-out processing. So the driver in Cosmos DB, which is known as PyDocumentDB or PyCosmosDB.Spark in the Java world, uses a push-down predicate logic to target specific nodes in the Cosmos DB, and nodes in the Cosmos DB are also known as partitions. So from a specific worker node in Spark, you can target a specific partition, making each of them parallelizable in terms of data processing and data consumption. This is a driver that we maintain on our own. Many Cosmos DB technologies rely on the open source community to provide the features and provide the functionality that is necessary for the community itself, but this is maintained by the Cosmos DB team itself. So in this case, the Spark layer is used for both the stream and the batch computing processes. In this case, we can use Apache Spark in a streaming capability and in a batch computing scheduled jobs capability through Databricks. Databricks will provide the infrastructure that will orchestrate how data is processed either by scheduled jobs or by the means of dealing with the streams that are sent directly to it. So I have a quick demo to show an example of this infrastructure. Why is this? Sorry. I have a quick demo to show an example of this infrastructure as it is being implemented. So what we have here is a simulated sensor for buildings that include pollution sensors and it simulates an entire array of sensors inside of a building. Then it sends that data to event hubs. We actually hosted this on a testing platform, load testing platform, so to simulate this environment. We don't have a building that has sensors in it. We send the data directly to event hubs, which then is sent to Azure Functions to form the data and do some pre-processing on it. We insert that into the master data set, Cosmos DB, and we use Spark for both the batch processing and the streaming processing. So Cosmos DB change feed will be triggered every time new data is inserted into this model, and then that will be sent to the end user application, which is either an Azure web app. In this case, we're just going to see the data and the aggregates in Spark, in Databricks itself. And the results of the batch process will be inserted into another Cosmos DB database that will then be that are the materialized view of the views of the aggregated data. So let's take a look at how the components are set up. So we hosted the source of the data into a load testing framework named Locust. This generates around 500 requests per second, and there's two instances of it. So as you can see, it's generating around 1,000 requests in a second with different values for the censored readings. Now, on the Azure side, we have a Cosmos DB account reading the streams directly into a Cosmos DB collection and storing them in a materialized view. So you can see the shape of the streams are basically event data. You have a CO2 reader that provides a value of the readings, as well as a timestamp, a unique ID, and a device ID, which is used today for as the partitioning key. Then, in the app insights of this architecture, we can see that there's around 100 milliseconds that it takes to process each of the requests, and this means that this is the time that it takes from the data source to the data base in Cosmos DB through event hubs. And every request is usually around in a sub-second way, around 50 milliseconds for it to be processed. So in the end, you can see also this traffic in the event hubs layer, and how it is generated from the source of the data through event hubs into Cosmos DB. So on the other side, we have the Apache Spark in two notebooks. One of them is the batch processing layer that reads from the master collection and filters it by date, and then aggregates that data and provides the visualization here. I should hide this node because it has the access keys. But you'll see that the events that are stored are aggregated from a count perspective. And for example, there's another requirement of show various attributes of the first 20 events. This is still running at the moment, but basically it provides a view that obtains chunks of the data and then aggregates that in a batch way, and then serves that to your application. In this case, we're only showing it on Azure Databricks. The other side is the stream processing layer that basically, I should hide the same cell. Yes, I should hide it. The same way, the stream processing actually, every time new data is inserted into Cosmos DB, it will be sent from change feed and into Apache Spark, and then it can run stream data operations like the following. So in this case, we can query. Okay, I think there was a failure in the data just because I let the database grow too big. But basically, you can execute queries on the real-time data, and it'll return the latest insertions into the database. So as you may see, this only requires two components, Azure Databricks and Cosmos DB. So Cosmos DB will have both the master data set, the storage of the computed views, and the real-time data access. And Spark will have both the batch processing layer and the stream processing layer through change feed that is triggering this data flow in real time. So this is our demo of the batch processing and how it can be done through Azure components and mostly Cosmos DB and Azure Databricks. So right now, I would like to invite to the stage Ramsey. He works in Microsoft Supply Chain, and he has implemented a Lambda architecture through the use of Cosmos DB, Azure Functions, and many other Azure components. So please give him a hand. Let me know when you're ready.
Hi, everyone. Hi, everyone. So I'm from Microsoft Supply Chain, and unlike the product groups, you guys might see a lot of Hello World demos. Well, over here it's real world solutions. So we can definitely relate to your pain points. We've tried a lot of these amazing technologies that are offered by the cloud stack, and we know we've been burnt and we've kicked the tires, so we know what works and how to fine tune it. And we have a really close relationship with the product group. So if something doesn't quite work, we'll go and scream at them, and sometimes they'll ignore us, but eventually it works out. And so there's a bunch of things in supply chain that happen, from design to sourcing, and there's a lot of money to be saved. There's a lot of efficiencies that we could create. So I'm going to focus on manufacturing today. So there's I'll kind of set up the manufacturing process, and there's something called first pass yield, and essentially what first pass yield is just a KPI of the quality of the devices that are coming out from the lines. We manufacture them step by step, and then in some areas we do some testing. So, and I have kind of a visual view of that just to kind of help that. Oh, let me just go to the... Sorry about that. Okay, so imagine that we just manufactured, we did about 30 steps of assembly, and then all these stations are testers, if you will. And every single tester has a very specific function to test either a camera or audio. It's a very sophisticated device, an expensive device. And every once in a while, if there's an error, that is the opportunity to go and investigate. And if there's enough errors, your yield will start to go down. And sometimes it causes the line to get shut down, and that's where things can get really expensive. And that's why you need real-time data processing to help you stop the bleeding. Yes, we need data analysis to kind of see trends and see patterns, but it's also very critical to be able to kind of heal these in real time. Okay. So that's what I was saying. The opportunity is that we want to take preventive measures. We want to have more devices getting shipped out. We want less scrap. The more scrap you have more people focused on fixing the issue, people scrambling, not focusing on their actual first job. Okay, so this is our current solution. And let me say that we have implemented a real-time data throughput, so that's great. We put the fire hydrant in, if you will. But the problem is, I think we chose, for real-time, we chose the wrong set of technologies to represent the data. Right now, you can see you have the ingestion, and this is your typical type of real-time processing, where you go through Event Hub and Stream Analytics, then you put it in the lake. The problem is what we're doing is that we're taking this real-time data, we're dumping it in a lake, and then somebody comes along with a bucket and just, says, okay, let me look at it. And so at the bottom layer, it's taken us 2 to 4 hours from end to end until it gets to Power BI. And the factory managers and the product engineers are saying, I can't work with this data. So I have to fall back on my older systems that are on-prem to find out what's going on. So that is the ingestion compute of the existing. And then now comes your real-time ingestion compute using some of the newer technologies, some of the newer patterns. So it's same exact fire hydrant, but this time we put a fire hose. And we brought it from 2 to 4 hours down to 2 to 5 seconds. And you can do this too, and it's actually cheaper than the first option, believe it or not. It's less complex, and it allows us to be super agile and to continuously experiment. And at the center of all this is Cosmos DB. We're using it for staging, and then we're using it for our master data set, as Luis was talking about that. Our Azure functions are ingesting the data, and then they take the complexity, the hierarchical type of data structures, and they reduce it to just what's needed, and they stage the data. And the best part of what I love about Cosmos is these event feeds. They allow us to kick off another process, which is this main set of functions that are doing the calculations. So to give you a perspective, we spent maybe 85% of our time in the calculations, making sure that we have the right algorithms and that we write tests. The previous solution, no tests. Now we have tests, it's very valuable, we can be very confident. So everything else on the left, plug and play, configuration, allowing us to just focus on the customer and the business problem. So I'm going to just kind of dive into what's happening in that calculation. I want you to see how much we're doing in that and how fast we're able to do it. I'm connecting to all that raw data, the staging data, and then I'm pulling in a bunch of master data sets. And the secret sauce here, guys, is storage is so fast now. You can put your master data in there, and there's ways to query it, and sometimes you don't even have to put, just the name of the file can give you a hint, can give you master data, believe it or not. All comes back under 100 milliseconds. So we're doing all these calculations. At the same time, we're pushing the failed operations. So all the data that's coming in here are the operations that you guys saw coming out of the testers. And we're able to fork in real time. So we're saying that I want to take the failed operations and I'm going to fork them off to Event Grid. Event Grid allows this pub-sub model, and you can imagine you can have as many subscribers that are interested in these failed operations to do whatever they need to do with it. All this in n instances. So we can imagine that our parallel processing is happening over 60 functions, if you will, and it's all happening under half a second. Super fast. All right, so we talked about the ingestion, we talked about the compute, and this is the consumption layer. And this is kind of where it's this similar Lambda architecture. So there's only one place that we do the computation, and then everything else trickles down to warm to cold. And so we have the different layers here. We have the real-time processing. When we push this stuff to Event Grid, we have another function app that's listening as a subscriber, and then it's doing two things. It's forking. It's saying, I'm going to be able to catch anomalies, and if there's a threshold that's been crossed, I'm going to let the bot go and let folks know that, hey, your project or your line is down, or the yield is dropped significantly. You need to go take a look at it, and here's the data. And the other one is we have a Signal R solution, which is awesome. It's a real-time UX service, and allows you to push it to as many clients as you want, all at the same time. They're seeing the same thing. And then a warm path, so as we're calculating the data in the function app that I showed you previously, we push it out to queues, which are then consumed and pushed into SQL. That goes from warm, and then that trickles down, and it goes into a cold store, where they can view and they can do historical analysis on that. And the one thing we're experimenting with now in real time is that we have a third Cosmos DB collection where we're going to put some cognitive search capability. And that is something that's preview. If you guys haven't heard, I encourage you to go read about it. It allows you to plug in your cognitive skills, which means you can enrich your documents using your machine learning algorithms in real time. Okay, so just to cover some of the benefits we saw from this type of pattern, lower costs, significantly lower costs. The development efforts were trivial. We didn't have to worry about a lot of the overhead. Again, we went with the serverless options. For us, we care about business outcome. We could care less about creating frameworks. We don't care for that. We're here to solve business problems. We need to lower the costs of what it takes to manufacture products so that the consumers can benefit from lower product prices. And we want to get stuff faster to market. We want to experiment, turn things around. If things are working, we want to turn that around and push it. And then the complexity was a lot lower. We can maintain this type of pattern, this type of solution, hand it off to other folks that are coming into the team. And the best part is the rerunnable unit tests. Before, we didn't have any rerunnable unit tests. So I'm going to just quickly show you a demo. And this is the Signal R component here. And all this data it's coming in real time. Every time you see that uptick, that's a message that's 3 seconds old that just came from China. Okay? Right now they're a bit slow, but that's because it's the weekend, so it's a lot lower volume. And we don't produce fruits, by the way. This is just we're kind of masking the names. Otherwise, I'll get fired, perhaps. So we're just masking the names, and you can see here that we're calculating yield. Again, yield is that kind of business view of what quality is. And somebody sitting in the factory floor can say, oh, okay, I'm seeing that this particular dip here, I don't like it. They might want to be able to get more information about that. So I have another one here that, just 1 second. So what the user can do now is then, click on certain parts of this report and then drill down. We'll get them the specific data because we have the store in real time. And then they have a breakdown of other types of information as well, failed by project, operation type, assembly state, you name it. So again, this could be running on any client because SignalR can push to any client. And yeah, that's all I have, guys. But with manufacturing, again, agility is key. Being innovative is key. We use the latest technologies, and we tested them. Everything we do now, what you saw was in production. That was not a demo. It's all data from production. Thanks very much for your time.
Thanks, Ramsey. So what we just saw is how Cosmos DB can be implemented as a master data set, and one of the consumers that can be SignalR, and how it can have close to real-time data processing and conclusions that can be obtained from it. So that's actually all we have for now. We can open up the discussion for a Q&A. There's some microphones out here on the stage, closer to the stage. But other than that, please feel free to tell us what your questions are.
This was great.
Thank you.
One of the questions I had for you guys, looking at the architecture for your ingestion points, you guys are using Event Hub and Azure Functions.
Mm-hmm.
Why not IoT Hub and Stream Analytics to at least get the data to Cosmos DB?
Yeah, so that is a great question. The question is, why not use IoT Hub for the specifically IoT data that we were showing in both of the demos? I don't know specifically about the supply chain. Do you want to chime in? The other one is just a demo. We wanted just to just simplify the architecture that we were just going to show.
Okay.
Actually, IoT Hub is for IoT data. And IoT data is, for us, it's like sensor, device sensor, or machine sensors, like temperature, you name it, that type of stuff. What I was showing was operational data. That is the result of the test that those machines were executing. So you have to try to separate those two different types of data sets. And we definitely have IoT Hub, and that's, like I said, it's for the sensor data.
So the operational data that you have, it's pretty much the event-driven data from a certain shift or line that's coming in?
Yes.
Okay.
Yes, on every single device. I mean, you can imagine hundreds of devices on many different lines are getting tested, and that data needs to be streamed out. It's complex data. It could be very, very large. Mm-hmm. IoT Hub has got a size limitation, so you can't use that there.
Okay, thank you.
You're welcome.
Yes.
One question I was thinking you have used event hubs anyways to get the events or messages. And I was thinking we could use Databricks directly point and consume from there. Maybe I missed a part where why would I have an extra hop in Cosmos DB and go to the change feed to get that streaming data? I can directly consume from event hubs because we are using Databricks Spark, right? Which is well integrated with event hubs too.
Right. I mean, the point was not the integration itself, but how you can have the same data set be consumed in two different ways. So Databricks still needs a data store if you're going to use batch aggregation. And so, sure, you could have implemented a Lambda architecture where the top part uses the master data set that uses Cosmos DB, and the flow to the bottom could have just read it directly from Spark. But just to allow for less complexity on the data, and since the data is the same, you don't have to send the data to two separate sources, but just one source, which is Cosmos DB, just to simplify the process itself. So that is one of the reasons why. Sure, in reality, and just like we saw in the Microsoft supply chain case, you may want to have multiple data streams going either to the master data set and then another path going directly into streaming, just to reduce that latency a little more. But then you have to maintain the multiple data streams on their own and see if the data, assuming that it's the same data, will be in sync on both versions. Like if both versions are actually providing the same level of reality. So that split of the data will be something you'd have to maintain, assuming that the data comes from the same source. Yes, we'll be hosting. This example was also used in another Cosmos DB session. Both will be packaged and hosted on GitHub. Not the one from Microsoft Supply Chain, the one from the Databricks notebooks and the sensor data simulated from this infrastructure. I'm not sure. We'll say, I think, right. We have a Cosmos DB central repository, so all examples are just hosted there. Yeah, so if you go to GitHub and then under Azure, not Microsoft, Azure, there's a set of Cosmos DB prefixed repositories, and that's where everything can be found. Sure.
I have a question.
Where's that come? Oh, yes.
One of the things I saw in the slide was you push it to the Cosmos DB and then push the RSS updates to kind of update the other pieces. What do you think about having another piece, which is Event Grid, which is kind of publishing the updates from Cosmos DB? Hey, some data change, you integrate that with Event Grid, and then Event Grid automatically takes care without having the RSS feed. What do you think about those two architectures? Like, can that be done as well?
I'm sorry, I don't think I understand where Event Grid actually is placed in this architecture. Would you mind clarifying that?
If you go back to your slide, right, where you publish the RSS feeds.
Oh, for the demo?
Yeah.
Yes.
There was some place where you kind of notified that there is a change in the database, and then you use the RSS feed to place those updates. Can that not be modeled on an Event Grid topic itself and say, hey, there is a place an Event Grid data type and say, hey, there is a change, and now you place the updates into the process that's listening into rather than going through the RSS feed itself?
Oh, change feed, you mean, not RSS feed?
Yeah.
Gotcha. I was like, there are no RSS feeds here. So why not Event Grid instead of change feed?
Correct.
Just because it's another separate component you'd have to maintain. Change feed is already enabled in Cosmos DB, and I can think of an answer in a couple fronts. One of them would be scalability. You have more guarantees in Cosmos DB than most other Azure services in terms of comprehensive SLAs, availability, things like that. And from a cost perspective, as a separate component, you'd have to deal with the charging of that component, as opposed to in Cosmos DB, this is already enabled and already ready to be used. It just works out of the box, and it's, I would say, simplifies the model. But if there is a need for an event grid component, it would have to be specific to that exact workload. As you may see, we actually added a few other components on this example just to give it some more of a real kind of point of view. The most real one, it comes from the supply chain example that was given, but this is a little bit more simplified. We just added the event hubs as a message processing queue. It could be Apache Storm. It could be there could be a lot of solutions that could be applicable for that. But if there is a need for event grid that is not served by change feed, I would say that could be offset by the cost of hosting event grid and the variability by using another service as opposed to just Cosmos DB. Thank you.
All right, so what are the defining characteristics of a Lambda architecture that makes it different from well-established architectural styles like CQRS or even CQS for that matter?
The main defining functions.
Like what's different?
Let's see, let me think about it this way. Well, Lambda architecture is just a proposal that is being now shared as a mean of a best practice, right? It's not a technology. It's a pattern. It's like a client-server pattern. It's like, and applicable to any sort of implementation detail. So the idea of a Lambda architecture is that you have two separate data needs, real-time and aggregated, and as a mean to separate it is just a proposal that uses separate components to process that data. So my answer is basically, it is a proposal, not an implemented best practice prescriptive guide to solve a problem. Right, so that's why it's not a comparable. That's why it's not a comparable. It can be comparable to an existing architecture.
I'm fairly new to Cosmos DB,
Yes.
but in SQL you have temporal tables, right?
Yes.
What's the equivalent in the Cosmos DB world? Do you use the change feed to kind of do something like that?
There is no equivalent of temporal tables in Cosmos DB. So Cosmos DB is a document store with multiple interfaces on top of it. Non-relational database that depends on manipulating JSON objects known as documents in the database backend.
But could you use this change feed to kind of simulate to get to that, to get audit history of records?
Sure. So the way change feed could be used in that sense would be by the mean of another collection, right? So it's not directly equivalent, but a collection could be translated as a table. And you can, we have a couple features that make the functionality of that table be closer to what a temporal table could be. We have a setting that's called time to live that would flush that table based on a specific period of time that is set unique to every single collection. So assuming that you want to push, I'm assuming this is in the use case of using a temporal table as a materialized view of aggregates. You can store that in another collection, and then that collection can be flushed using the time to live setting for it to provide functionality that is similar to that. But in itself, it is not an equivalent technology to a relational database. Okay, sounds like, unless there's anything else? Nope, okay. Cool, then it seems like that's all. Thank you very much.